Okay, this is problem 15.1. First question asks, which of the isomeric C4H10O alcohols can be prepared by hydrogenation of aldehydes? So the first up top is these two isomers for the aldehydes, and both of these after reduction go to the alcohols as seen here. And those are two that work for aldehydes. The next question asks the same but for ketones, and this is one example of a ketone that would work for reducing or preparing the hydrogenation of ketones. And one thing to know for when preparing alcohols by reduction is that tertiary do not work, such as this 2-methyl-2-propanol can't be prepared because it's a tertiary alcohol.
Okay, so right here we have 15.2. We have A through D. I already wrote out all the reactions and we're just going to go through them. This first one has an aldehyde with NABD4 with H2O. And so it's going to give you 3 of these right here. And so basically what it does is NABD4 is like Na sodium borohydride. And so anyways, so it reduces it as well. But instead of having an H where the carbonyl is, it's going to have a D, and then it's going to have the hydroxyl group at the end. So you can see this right here. And this is your side product. And then this one is the same thing. It gets reduced, and then you're going to have this OD come here at the end, like it has over there. And then right here, this carbonyl gets reduced. The D sticks out where the H would be, and you get the OH on the edge also. Down here, you have LiALD4 with diethyl ether, and then the second step is going to be D2O. For this one, you have 1 carbon right here, which is a CH2, and then this is a 4, so you're gonna have 4 of these, and so you're gonna have the D right here, where the H was, and then you're gonna have the OD on this one.
Okay, so this is problem 15.3. The problem is asking for appropriate Grignard reagents for each case. So first, we know that we have an OH, and we already know that we're going to use Grignard reagents. So something easy to use would be an epoxide. So first, we know we have this on. These are the products, and the reactants are going to be on this side. And let's see. CH3 is going to stay there the same, and instead of CH2, CH2OH, we're just going to use a Grignard here. So it's going to be NGBr, and we're going to get these 2 carbons using the epoxide. So we're going to react this with ethylene oxide, which is like a little triangle, and we use diethyl ether and H3O+. Okay, so what happens is the Grignard comes and attacks the carbon, and this comes down, knocks it down, and then the oxygen later comes, in the next step, the oxygen gets protonated by the H3O+, turning into an alcohol. For problem B, it's basically the same thing. It's just a cyclohexane this way. And same thing, it's going to be the MGBr using the Grignard reacting with an epoxide, ethylene oxide again. And the same thing again, diethyl ether and H3O+. So again, the Grignard will come and attack the carbon, knock the electrons down to the oxygen. The next step, the H3O+ will protonate the oxygen, making an alcohol on the cyclohexane ring.
So this is 15.5. We have an A and B kind of thing going on. So we have a cis and trans of butene. We have the cis, trans, And so we use these reagents right here to put on the OHs. And so when you have a cis with the CHs on the same side of the double bond, you're going to have CH3s coming off on that same side without the double bond, and you're going to get the OH from the reagent. The trans one uses the same reagent, so I didn't copy that down, but it's the same one. And for trans, you're going to have one methyl and another methyl opposite sides of the double bond. And so when that comes out, you're going to get racemic mixtures. So this is one that you get, and this is the second one. The CH3s are still on the opposite sides of the bond, but it's racemic because you can get the CH3 here dashed, or you can do the CH3 wedged. So that's why it's racemic, and that happens with the trans. And that's it.
Okay, this is 15.6. The question is asking that the trans 2-butene was subjected to dihydroxylation. The 2,3-butene diol that was formed had the R configuration at one carbon, and the question is asking for what was the configuration at the other carbon. So what happens is when trans 2-butene or butene goes through dihydroxylation, the OH is formed on both sides from the double bond. If it's a trans, this is cis form, and this is the trans form. And in this particular situation, the priority group is a hydroxyl, and then the carbon, because there's 2 carbons in a row as opposed to just the methyl. So this would be the last group, and if you group it like this, 1, 2, 3, it's going to be counterclockwise, which is going to be an S form. So both of these are going to be S. And the other one, when after dihydroxylation, is going to form a trans bond, and it's going to have, or it's going to, not trans, but the stereochemistry is going to be both R's because the hydroxyl again is priority, and the 2 carbons take priority over the 1 carbon from the methyl. When grouped like this, the 1, 2, 3 go in a clockwise position, so the stereochemistry is R. And so the answer to the question is the configuration at the other one is going to be R.